Hello, my name is Artyom. Let's start with the first task. I import OS, I import pandas as PD. So this Bayesian network implementation for predicting gen inheritance. The idea is we have a family, mother, father, child, and each person can have 0, 1 or 2 copies of a specific gen. For example, the gen that causes the hearing problem. We know who shows the trait, but we don't know exactly how many gens copies each person has. So this program job is figure out those probabilities. We have some data in three CSV files, family 0, 1 and 2. Here we load from file name. Here's the file name pass. We load with pandas, and each one is a different family. The columns are name, mother, father, and a trait. The program loads these files using pandas, and we next have probabilities dictionary here in the start. So we have three things here. First, unconditional probability of having 1, 0 or 2 gen copies in general. So it's 96, 0.003 or 0.1%. Then we have trait. If we have 2, it's 65%. If it's 1, it's 56, and if it's 0, it's 0.001 because of mutation. So then we have the main function in the whole program. It's this one. Joint probability. Here it calculates the probability of one specific scenario. For example, let's run the file. For example, we have Lily, James, and Harry. Lily has 0 copies, James has 2 copies, and Harry has 1 copy. And James shows a trait, the other don't. So, for children, we calculate what each parent passes. If a parent has 2 copies, they pass the gen with 99% of probability. If 0 copies, only through mutation. So 1%. If 1 copy, 50-50%. We multiply the probabilities from mom and from dad to get the child gen probabilities. Then we multiply by the trait probability, and all of this get multiplied across the whole family to produce one joint probability. Here how it calculated, and then we multiply gen probability to trait probability, return prob. So then the program loops over every possible combination, who has how many gens, who shows the trait, and for each combination it calls joint probability and add result to running total in the update function. So here it added and create a sum for each probability in normalize, and then we calculate the 100%. Here update function it summarize, normalize, calculates in the percent. So in the program process, all three families has trait equal to 1. We know this for certain, so trait true is 1. So Lily has trait 0 and it's false. Harry is unknown. The program calculated here 45% for one trait. So 27% chance almost that he will have hearing disease. So let's move on to the second. So task 2 is about predicting flying cancellation. I'm using two approaches. It's a knowledge-based engine and bias theorem from probability. First, the dataset has flights. The main column is cancelled. 0 means the flight happened, and 1 means it was cancelled. There are also cancellation code. The reason A is a carrier issue, B is a weather, C is a air traffic control, and D is security. From the raw data, I gained 2 extra features: time of day, here how I calculated it, from the scheduled departure time, morning, afternoon, evening or night, and a distance category, short, medium or a long. So the first component is the knowledge base agent. Here how it looks like. It's a dictionary called knowledge base that implements logic rules. The rule looks like this. If the cancellation code is B, then the cause is weather and the risk is high. If the code is A, carrier issue, risk is medium. And the propositional logic here is simple. It's if something, then something. And if weather, then high risk. Then we have the logical inference and infer from code. Takes a code and returns the cause and risk level. We apply it to all cancelled flights and can see the weather is the most common cause. Let's run here. We can see that weather is the most common cause in the cancelled here cancellation code B95. So it means that 95 flights were cancelled because of weather. Next, I classify airlines by risks. So I calculate the calculation rate. 1 second. Here, classify airlines. For each airlines with rate 1 point time above average are high risks. That's G4 and YV. 1 second. Here. Here. And low risk airlines. It's all others. It's below 75% of average. Then the logical inference function applies the rules. If it's a high risk airline and a night flight, it's very high risk. If it's a low risk airline in the morning, it's a low risk. So this is a logical inference in action. The second component is a bias theorem. It answers the question what is the probability of cancellation given that we know the airline and time of the day. So by bias theorem, the probability of cancellation given the evidence equals the probability of the evidence among the cancelled flights. It also multiplied by the base cancellation rate divided by the total probability of the evidence. It's a formula with ascending false. Here is how it looks like. And in practice, we look. 1 second. How often G4 appears among cancelled flights versus normal flights. So here we also can see the cancelled flights. More of them is in the evening. And bias prediction, airline G4 not cancelled, high level. So the predict fly function combines both approaches. First, the logical inference given a risk level, and the bias theorem that computes the exact probability. If logic say high, we slightly increase the probability, and if it's low, we decrease it. The output is a final prediction, cancelled or not. So if we run it, we can see here in the that 2.4% is cancelled and 97% is not cancelled. So bias theorem give us precise numbers, and the knowledge base agent add explanations. Why exactly the flight is risky, where and when it's risky, and which one are most riskiest. Together they form a complete AI system for predicting flight cancellations. Here.